So in Mod 2.3, we started talking about linear equations and that constant rate of change. Remember that slope. And so that's where we're going to continue looking at different applications of that. So let's read over example number 3. It says the owner of a swimming pool wants to know the rate at which the depth of the water in his pool is changing. When he begins filling the pool at noon, there is already some water in the pool. At 2 p.m., the depth of the water is 21 inches. And when it's 5 p.m., the depth of the water is 32 inches. So they've made a little table there, okay? Assume that the depth of the water in the pool changes at a constant rate of change with respect to time elapsed. What does this mean? Did anybody give me an idea of, in A, what are they referring to when they say that the depth is changing with respect to time at a constant rate of change? What does that tell us that they're really looking for? Yeah, so you can say that this is really going to represent our slope. And in this particular application, it is the change in depth of the water. So I'll call it H for height, I guess. And then the variable for our x's, remember it's y's over x's, would be time. Now, in B, it says, what is the change in time elapsed from 2 to 5 p.m.? So let's actually write it as a delta t. Now remember, it's always going to be the final version, 5, minus the initial. So it should be 5 minus 2 or 3. Always keep it in that order. It's always ending minus beginning. Otherwise, you might get a negative value where you shouldn't, or you may not get a negative value if you do it wrong. So the change in the depth of the water in the pool over that time. So let's talk about the change in depth. We'll call it the change in height. Okay, so we know that this delta t we found to be 3. Now let's calculate the delta h. What is the height of the water at this particular time? Well, the ending was 32 because they're filling up the pool, minus 21, which is 11. And let's put our units on this. Okay, so this was hours, and this is inches. And then if we move on to C, it says, assuming a constant rate of change, how fast is the depth of the water in the pool changing? With what is the rate of the depth of the water in the pool in inches with respect to the number of hours since the pool has been filling? So we're talking about the change in height over the change in time, that slope, that constant rate of change. So it would be 11 over 3, and that would be inches per hour. So every hour it changes by 11/3. Now I know 11/3 isn't a great number as far as its decimal keeps on going. It is 3 2/3, 3.666 repeating. So when we actually have to put our values in the chart, if we want exact values, we are going to need to use the, I would probably use the improper fraction, but we'll deal with that in a minute, okay? So it says to create a formula to represent the depth of the water in terms of the number of hours. So we're going to have H be the height of the water, or depth of water, you can call it. So if you use D, that would okay. And then T, we're going to define that as the time in hours. And so we know if we think of y equals mx plus b, our time is our independent variable. the depth of the water is our y value or our dependent variable. So our equation would be H equals 11/3 T plus our starting height, which we haven't figured that out. So let's put just a little b there. And then we are going to fill in the chart at the top of the page, and then we're going to get that b value because they didn't tell us, but up in the chart, that is that value right there. Okay, so we're getting there. Okay, so every hour it goes up by 2. So if we go backwards in time, or up by 11/3, so every hour that we go backwards in time, the pool would go down 11/3. So if we see this, we've gone backwards 2 hours. So we have to go backwards 11/3 times 2. So let's think about what that is. 11/3 times 2. I say one thing, but I read it. Times 2, just put that 2 over 1. That's 22/3. So we have to take what we were at the 2-hour mark, and we have to take off 22/3. So let's remember how to do that. So anytime you're doing a whole number, subtracting some type of fractional thing from it, just put that whole number over 1. And what's great about this is we always kind of do the same thing. Just multiply the top and bottom by the denominator we see in the one that started out as a fraction. And so this would be 63/3 minus 22/3. Now 63 minus 22 is 41/3. So we can put 41/3 as our answer, but let's give it a decimal because we are going to have to put it on the graph paper. So 41 divided by 3 is approximately, and I like to use when I have rounded, and I'm sorry that's so ugly, but if you use an equal to sign that's wiggly instead of straight, that tells me that you have rounded it. And so that is customary in math. If you have rounded something from the exact answer, if you just put that wiggly mark there, you've told me that you've rounded it. Now on a graph paper, even going to the nearest tenth is difficult, but let's take it to the nearest tenth. This is 13.7 inches. Okay. Now this one from here to here, that has gone up by 1. 3 minus 2 is 1. So this has to go up by 11/3. So 21 plus 11/3, if we did the same technique as far as getting a common denominator and all that lovely stuff, let me tell you what it was. It'd be 74/3, which is approximately 24.7. And then they already told us the 32. This goes up by 3. So 11/3 times 3, which is great about 11/3 times 3, is the 3's cancel. So we're just going up by 11. So if we go up by a factor of 3, then we get a nice number to add. So we can just add 11 to 32. 11 plus 32 is 43. And then at the 13,
it's 8 hours, not 6. So wouldn't you need to add 11 a couple more times?
so from here to here, so I was going from the last one I knew, it went up by 3.
Oh,
So yeah, if you were going back to another one, you would have. I just picked the one that was next to it, that since it was a nice value, that 32. So since that went up by 3, remember the constant rate of change means it's going to go up by 11. So that was nice in that particular case. So if it was, if you went backwards like Yes, if you went all the way back to the 2, yes, you would do 22, I think. You would, because it'd be 6 and then it'd be 22, I think. Okay. And we can even check the work. 43 is 22 away from 21. Okay. And then finally 13 is going to be a weird one. Okay, so this goes up by 5. So that's 5 times 11 thirds. It has to go up by 55 thirds. So 13, 43 was where it left off, plus 55 thirds is 184 thirds, which is approximately 61.3 inches. So a little strange because that 11 thirds is pretty yucky. You can set up a proportion each time. If 3 hours is 11, or I'm sorry, if 3 hours is 11 inches, then 5 hours is how many inches, and that could also tell you how much to go up. Yes.
By the way, technically with the table,
Uh-huh.
we don't really need to add the inches to that because it says inches at the top.
That is true. Yes, yes, they have given us that at the top. I'm just reminding you that these ones, remember, are hours and those ones are inches. Thank you. Okay. So now we've got our table filled out. I am going to let's take, and you might want to do this too on your paper. I'm going to use that little capture tool to copy it because we're going to need it down here. Okay, so if you want to do that so we can have that chart down below, just use that. The capture tool is the one that has the little dots around it. And if you do the capture around the image and then just paste it as an image, you'll paste the background chart and the numerical values. Okay. Now, that leads us to G. It says construct a graph that represents the depth of the pull in inches in terms of the amount of time in hours. So see where it says in terms of, that means the in terms of one is going to be our X value. So this is going to be time in hours. And this is going to be the depth in inches. So remember, you want to label your information. Now, both of those pieces of information are positive things. That's why we only need the first quadrant, the positive positives, which is good. Okay. Now, the points that I see on the original graph, there are 3 points that are really, really nice. So let's put those 3 points on. Now, I have to get up to 43. So let's count. Let's go by 5, or up to 61 actually. Let's go by 5s. So that would be 10, 20, 30, 40, 50, 60. So on the inches, I have to go all the way up to 61. So I'm going to do that for my X's. If you decided to count a different way, like I think when they did it, when I noticed the answer key, I think they were counting by 8s, which I found kind of, yeah, 32 goes into 8, but I don't know. I counted by 5s. Okay, and then on the our x-axis, our time, we just can count by 1s. So we can count by 1s, and I'm not going to show all those obviously, but I'll go all the way up to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we got our graph paper ready to go. So let's put on the 221, the 532, and the 843. They should form a linear equation or we have done it wrong, okay? So at 2, we're just a touch over the 20 mark. At 5, we are just a touch over the 30 mark. And then at 8, we are a little bit more over the 40 mark. And you can see they pretty much are going to form a linear equation. We have to go until we hit 13. So we started at a height of 13.7, which makes sense based upon our numbers here. And let's go up to the 13 mark. Maybe they stop filling it after that. And that should be the 61.3 mark. Obviously, I didn't line up perfectly. It's pretty close, yeah. Okay. So that is our graph. Now, I've noticed in the young man I was working with on iMath this morning that sometimes they will say, put this particular point on the graph. That's the only one you use the point feature. And then they'll say, or they won't say much, but if they have the little line graph tool at the bottom, make sure you put the line that should be on the graph through those points, okay? Do we have any questions about example 3? So hopefully that will help you as you go through these next 2 homework assignments, okay? We're going to talk just quickly about some of the formulas you should know. We have talked about these on and on, so I didn't, you didn't have to really write those down, but highlight the fact that the ratio of our constant rate of change should be the change in y over the change in x, where the constant rate of change, remember that is that slope. So you can even put a word here, slope, to remind you that that is just a fancy way of saying slope. It is going to be delta y to represent the change in y and delta x to represent the change in x. Remember, it's always the ending value minus the start. So y2 minus y1, ending value minus the start, x2 minus x1. Okay, that is the constant rate of change of y with respect to x. Y will be our dependent variable. With respect to means it's dependent upon the x that we have chosen, okay? And then here they've just kind of told you a little bit more about that concept. I noticed this, they rearranged to find the change in y. They multiplied the slope by the change in x, and that's pretty much what we were doing in the formula, but I wasn't really writing it out in that particular way. But that's a good way to think about, if I know how much it changes in the x, if I multiply the slope by that, I will find the change in y. So that's a really nice one. Make sure to highlight that one, okay? Okay, so now let's take a look at 5. And we're going to create a graph. We're going to do all the things they tell us to do. Okay. It says, given that x and y are changing together at a constant rate of change, so that means it's a linear equation. And then it says that delta y is -2 delta x. So let's take that equation they have given us, and let's solve for delta y over delta x. Let's know what that slope is. Or you can recognize that if I move the delta x to the other side, I know my slope is -2, okay? And it says this rate of change occurs when x is 1 and y is 7. To graph any line, all you need is a point and a slope. Yesterday, I told you there might be some formulas that are useful. Here's one of them. Y minus y1 equals m times x minus x1. It is called the point slope formula. It allows us to find the equation of the line as long as we know a point and a slope, which we do know in this particular case. Now, let's take a look at part B. And then we'll talk about the equation here in a second. We'll use that formula. It says, but part B says, as x increases from 1 to 5.5, how does y change? Illustrate these changes on your graph. Okay, so let's go to the graph. Let's find the point, and I'm just going to count by ones. Find the point 1, 7, which is right here. Our slope is -2. That is rise over run. So we're going to go down 2 into the right 1, down 2, right 1, down 2, right 1. They did not say any application for this, so we do not know if it's restricted to that first quadrant. So we're just going to stretch it across your entire graph paper. Now, I am a horrible straight line grapher, so I do tend to use that tool. If you're making your graph of your line, if you just hold in the pencil before you release it, it will try to straighten it for you. And then just try to hit the points that they've given you. Okay. So as x increases from 1 to 5.5, we know that delta x is going to be 5.5 minus 1, or 4.5. So if we want to represent that on the graph, if we go where x is 1, that's the point up here. I've highlighted it kind of in a yellowish color. And then if we go, that means our x is increasing from that point. Our x increases as you go to the right. Just make a little arrow, 1, 2, 3, 4.5 to the right. Now I've almost hit 5 because of the chubbiness of the line there. That's a little better, barely. Let's do it one more time. I'm just trying to hit that for you real good. 1, 2, 3, 4.5. Yeah, that's a little better. Okay. So that's how you would illustrate that change on the graph. And it says, does x take on all values between 1 and 5.5? If so, how is this illustrated on the graph? As you can see, this portion of the graph takes on all x values between that x value of 1 and the x value of 5.5. So yes. How do we illustrate that? As I drew that portion of the graph, as I went from an x value of 1 to an x value of 5.5, I never had to lift my pencil from the graph. So if you don't have to lift the pencil to create it from point A to point B, all the values from there to there are included. We call that part of the graph a continuous portion of the graph. So that's really what they're asking and see. Is that a continuous portion of the graph between 1 and 5.5? Well, yes, it is. I didn't have to lift my pencil. It's a perfectly connected portion of the graph. So that's why it's the yes. Everybody okay with 5? Yes.
So can you show me what it wouldn't look like if it didn't take on?
Oh yeah, sure. I mean, anything that has a break. So if you have a graph and there is a disconnect, that's one example. If you have a graph that just happens to have a hole, if you have a graph that as you get to that spot, there's something called an asymptote. That's another example. So that's really kind of the only time that will occur. But I think a really good visual is if you think about, if I drew that, do I have to lift my pen? Because in this case, as I drew that, I have to lift up my pencil to make the other piece. And so that's really just a good way to think of it. There's really 3 types. There's a hole in the graph, there's an asymptote in the graph, or there's a piecewise function where the pieces just aren't connected. So that is a good question. Okay, anything else for number 5? Okay. And then number 6. It says the given graph represents a linear relationship between y, which is Bob's distance in miles to the finish line of a race, and x, which is the amount of time in minutes since Bob passed the final water station. Okay, so stop. We need to go backwards for a minute. Go back to here. I told you that there's an equation or that we can find the equation of the line, a formula. So in this particular case, we know our slope is -2 and the point is 1,7. What's great about that equation is we can just plop those values in and we know the equation, the formula for this particular line. So it would just be y minus 7 equals -2 times x minus 1. Now, if you wanted to isolate the y, that's very common. Just distribute that -2 and then add 7 and you got it. Just rearrange it a little. But I'm sorry I jumped ahead, but I did want you to see that really highlight that. That's a really great equation. I use it and suggest my calculus students use it all the time. So as we prepare for calculus, hopefully in your future, that's a really great tool because it's so quick. I know the point, I know the slope, bam, just plop it in, you got it. Okay. So now what it says in number 6 is we have Bob's distance in miles from the finish line of the race, and x is the amount of time in minutes. So it's not a bad idea to make yourself a little summary of what they told you, that our x's are minutes and our y's are miles. What does the point -22, 8.2 represent? So that's why kind of summarizing it like that on your paper is just really helpful, because that means that it says the amount of time in minutes since Bob passed the final water station. So he passed it 22 minutes ago. I would assume that's what that -1, like it was in his past. He passed it 22 minutes ago. And he is 8.1 or 8.2 miles to the finish. Now, what B is saying, I think the negative would be he will pass it. Sorry, in 22 minutes, because the positive then wouldn't make sense if he only has 2.2 to go. He will pass the final water station in 22 minutes, and he has 8.2 miles to the finish line, because 3 means he already passed it. So he's 3 miles past it, a positive thing past it. 3 miles or 3 minutes ago. And he is 2.2 miles from the finish. And then determine the m, or the slope value, the constant rate of change in this linear relationship. So this is a good one about using a formula we talked about yesterday. That's your change in y over change in x, or y2 minus y1 over x2 minus x1. So they gave us 2 points. I always think of my x value as the determiner as to which one. So I kind of go from left to right. So we're going to make this one our x1. So this, of course, then would be our y1. And this is our x2, y2. Okay. So I always go from left to right. That will help that your denominator will always end up being a positive value that way. So it'll just help the function of things pretty nice. Okay, so let's plop those values into our formula. So it's going to be 2.2 minus 8.2 over 3 minus a -22, which would become plus 22. 2.2 minus 8.2 is -6. 3 plus 22 is 25. Do you see how we got that positive value in our denominator, which is a great way to represent a fraction? The negative can be on top, but you don't want it in the bottom. Remember, at the top, the y's represented miles, and the x's represented minutes. Now, the negative is that distance we are closing in as we run to the finish line. And you can see the finish line will happen when we hit the 0 mark, the 0 for our y value. And then here we ask about writing the formula. So that y minus y1 equals m times x minus x1, I feel, is the most efficient way to find the equation of a line. We have 2 points to choose from. Both points are fine with me. And I know you know how to rearrange an equation. You should by this point. So I'm not going to do that part of things as long as you set it up. Now, iMath might have you do it, but for me, let's use our slope of negative 6 over 25. And I'm just going to use the positive 0.3, 2.2. So it would be y minus our y value, 2.2, equals our slope times x minus my x value of 3. And you don't have to go further, unless that bothers you the way that it looks and you feel that you want to rearrange. To rearrange, just distribute that in and then add 2.2 and then you got it, okay? But those are this equation, so important that you know. So know your slope formula, know your the point slope formula, and then every linear equation becomes a little bit easier. Do we have any questions about number 3? Or, oh gosh, number 6. The third thing we did, but number 6. Any questions about that one? Okay. And then the final page we're going to do here, it says, given that the x and y axes have the same scale, answer the following questions. So what I do is they want to find the constant rate of change. They want to find the slope, okay? Remember, that's just a fancy way of saying slope. So what I would probably do is I would probably kind of do a fake little measurement of that. And would you agree, I believe at least, how many of those do you think are there? Do you think it's 3 or do you think it's, yeah, it's really close to 4, isn't it? Okay, so 1, 2, 3, yeah, let's go 4. So wouldn't you agree that whatever those numbers happen to be, that our delta y over delta x would be 1 unit over 4 units? So, and it's positive because this is going in the positive direction, and so is that, okay? So if they don't give you the units, that's what you would say. I think, so that one's 1/4, okay? Let's do the same thing with this one. Now, that appears, that length, I say there's probably 2 of those there, I'd say. Would you say that that's probably, that length is probably 2 of those? But this is going in the positive direction, but this is going down, which is a negative. So our delta y over delta x, the y is going down 2 units for every one that the x is going a positive 1 to the right. So our slope there is -2. So that's a little bit how you can determine or approximate the slope, even if you don't have units. As long as they're counted by the same thing, then you can guesstimate. Yes. Yeah. Yeah, so we are comparing the lengths, and we're doing that very thing. We are guessing how many of the smaller one would be in it. This one I'm debating a little bit. Maybe it's somewhere between 3 and 4. So even like, if you put that you thought there were 3 of those units, and your neighbor friend said that it was 4, you're both going to get it, because we don't have the values. We have to guesstimate. We have to guesstimate exactly. And I've noticed that happens sometimes. The higher you get in math, sometimes you have to make that educated guess based upon the information you're given. Okay. It says write a formula that expresses delta y in terms of delta x. So let's write down the formulas that we had, please, down below. So what's weird is we're going to treat delta y and delta x as if they are like variables. And so if we want delta y in terms of delta x, we want it to say delta y equals all the other stuff, including the delta x. So all we got to do to change that is to just distribute that to the other side, multiply it by the other side. So this one would be delta y equals 1/4 delta x. This one would be delta y equals -2 delta x. So, and that was one of the things in one of those boxes earlier, that they had written. Okay. And then it says C, write a formula to express y in terms of x given the y-intercept of the graph of function A is 0, 3, and the y-intercept of the graph of function B is 0, -3. So if we know the slope is 1/4 and the point is 0, 3, y minus y1 equals m times x minus x1, or we know that it's y equals mx plus b. So you can use either of those for this when they give you the y-intercept, but this will become what we want. So I always tell my students just to rely on that point slope formula. So here our slope was -2. Our point was 0, -3. So we can do y plus 3 equals -2 times x minus 0, or we get y equals -2x minus 3. You can give me either of those versions for that particular problem. It's okay either way. So we have now finished mod 2-3i. Are there any questions before we turn this in? Anybody have any questions? Okay, so please turn this in. You have a nice chunk of time right now, at least a little bit, to be working on your iMath. And if you need me to walk you through any of the questions, you're getting stuck on a question, you're not being able to answer a question. If you were absent and you need a date extended, I need to know all that in the 10 minutes we're together, that you're working on iMath. So at this time, turn this into Google Classroom and work on your iMath, okay?